Thank you very much, Professor Wan, and thank you very much for the World Wood Day Organizing Committee for inviting me to this conference. It's very much something very special. I'm enjoying this event tremendously. My talk today will be on the structural characteristics of timber pagodas in Japan. Andrew just gave you an overall introduction to the many types of pagodas in East Asia. My talk will be especially on Japanese. In Japan, we have many types of traditional architectures, and most of our traditional architectures designated as cultural properties are 90% of timber structures. So our important cultural properties, the left-hand side is an old farmhouse, right-hand side is the pagoda that we are going to talk about today. And the structural characteristics. The structural characteristics of timber pagodas and timber architecture in Japan is made of a timber post and beam construction, and usually made with timber and mud, bamboo, and these non-engineered natural materials. And as I have referred to, we are facing a strong very, very strong natural hazard, including typhoons and earthquakes. So in Japan, when we say structural engineering, it is almost nearly equal to seismic engineering, how to protect these architecture from collapsing by earthquake. Just a little bit of statistics. This is the map of the world, and each dot, these dots indicate the event of earthquake. And you can see many dots, and Nepal is also a seismic country. But Japan is a very small island country, which is right here. You can't even see our country due to so many dots. And the number of earthquake, the area of Japan is about 1/10 of the world. We are a very small island country, but 1/200 of the world. But the number of earthquakes which take place is about 1/10. So we have a very high percentage, high density of earthquakes in Japan. And not only from these numbers, but you can see from the illustrations how much a seismic prone country we are. This is an old temple built in the 15th century, which was a national treasure. It collapsed entirely in the earthquake by 1923. And this kind of damage has been known to occur repetitively. But we have been buildings, beam buildings, but they have been damaged repetitively by earthquake. And concerning the timber pagoda that we are researching about, is that we have about 22 existing timber pagodas built before 1850. After that, we have been building more. And actually, timber pagoda is being built almost annually in Japan. So people like these constructions. But they're very, very complex, very high, and does not look so much strong against earthquake. But actually, these timber pagodas, 5-story timber pagodas, there is no literature of a complete damage, complete collapse by earthquake. So it has been sort of like a mystery why these vulnerable looking structures are so strong against earthquake. Traditional timber pagodas, they have been built since the 7th century. Many have been lost due to fire and lightning. And two has collapsed by wind, strong wind. But none has been known to have collapsed by earthquake. So many researchers have been trying to understand why this happened, why they are strong or not. But and I will just introduce a little bit of the recent researches that we are doing. Please let me give you a small description, a short description of how they are made. You have the center column in the center, and there is the metal ornament on top, which is quite heavy. And then there are the surrounding frame. And the most characteristic of all is that the center column and the surrounding frame is structurally independent of each other. So even myself, not so strong, if I go to the center and push the center column, it moves very easily because it is just standing on its own and only connected to the main frame at the top. So the other part is free. Another characteristic is that these surrounding frames, they are built each floor. So not only one long column in the center, and the surrounding columns are each very short. And there is we call them brackets. They are originally from China to support a complex element to support the long outstretching eaves. In Nepal, they have a very big, large member to support the eave. We use small elements and combine them together to support the eave. A little bit different, but basically the same. And our research consists of many things. I cannot introduce everything. I'm sorry, it would take 2 hours. So I will just introduce a little bit. The yellow one, which is the most dynamic. The outline is that we first investigated from literature survey, have they really been damaged or not? And the second part is the modeling of each elements. Like this is the joint, structurally that is made of column and beam, and the column and beam joint. The joint is very, very important concerning structure. Many different types of joints. And also the brackets that I showed you about to hold the roof and eave. And these elements have been tested dynamically and statically, and combining these elements, it is analyzed. But how does it move actually was our main interest, because nobody has actually seen a standing pagoda move under earthquake. So we wanted to do a structurally modeling test we did several tests. It's a very small measurement to earthquake monitoring and shaking table test and statically pulling test. I will show you the images of the shaking table test. We did this in 2004, so more than 10 years ago. We made a 1x5 scale model of an existing pagoda, put it on a shaking table. Shaking table is a device which can simulate the movement of an earthquake, and moved the shaking table. It was a very large group funded by many institutions. The same section and elevation. It was a 1x5 scaled model, but actually the original building is 30 meters tall. So the 1x5 scale is 6.6 meters, very big actually. And the weight we added on top for the clay tile roofing added to 2 tons. And the specimen arrived. This was not how it was made originally, of course, but at first the craftsman made it in the factory and they moved it to the experimental laboratory by truck. And we installed each story one by one. This is the first story, and the right-hand side is the master carpenter who made this building. And you can see the center columns in the installation of the 4th story. And it's finished 6.6 meters and 4.6 meters in the height. I will just show you some images of the experiment. this was the input motion of the Kobe earthquake in 1995. And you could see that it moved in a very curved wave. This means that it shows, from a special point of view, higher modes of vibration. So it is not moving like this, but moving in a very complex second mode, third mode of vibration. And we were able to monitor this, and this was a very important experience for us, because now we know how they perform actually. So this is the outline of the research that we are trying to do, and we are now trying to simulate the actual performance. But actually this is not so easy, and we are still testing each of the members and trying to simulate and do the same movement again. And lastly, I would like to talk a little bit about Nepal, as I am in Nepal. There was, as you know, a very large earthquake, Gorkha earthquake, last year, and we have investigated some pagodas in Nepal also, because we share the same interest with high-rise pagodas in a seismic-prone zone. So, in 2009, we operated some tests, on-site tests in Nepal, and unfortunately, on two pagodas, one was a Kumbheshwar temple, it's a 5-story pagoda. Unfortunately, this pagoda was damaged on the 5th floor, so it was originally 5 stories. This was the left-hand side picture is the picture taken in 2009. Right-hand side was the picture we took last year after the damage. So the 5th story fell off, unfortunately. And there is another 3-story pagoda, Radha Krishna temple in Patan. We also measured this pagoda. Unfortunately, this was totally damaged. So we are trying to understand why the Japanese pagodas, they have survived many large-scale earthquakes. But during this earthquake in Nepal, many pagodas suffered very heavy damage. So we are trying to understand the difference and the systems of the Nepalese pagodas together with the Japanese pagodas as in comparison. Okay, so this is all for my presentation. Thank you very much.